Okay, final question 6 then. The question is about elements in group 7 on the periodic table and their compounds. We're being given bromine, strontium chloride and iodine monochloride, and they all have similar molecular masses. We have to suggest with reasons the order of melting points for these 3 substances. Okay, so I'm going to go through each individual substance and just identify the types of bonds, the types of intermolecular forces. So bromine is going to have van der Waals forces between it. Strontium chloride, well, we've got a metal and a non-metal, suggesting that we're going to have ionic bonding. And then iodine monochloride is going to be covalent, but it's going to have dipole interactions. So when it comes to writing my answer then, I'm going to start with, well, first of all, thinking about the order of the melting points. So I know van der Waals is going to be the weakest, so that's going to be the lowest melting point. Then we'll have our dipole interactions, and then we will have our ionic lattice, and then I'm going to go through and explain each of them. So SrCl2 has very strong ionic bonds. It's actually arranged as a giant lattice. I've then got ICl, which is dipole interactions, which are weaker than ionic bonds. I've then got Br2, which is just van der Waals, the weakest. IMF. Now that is a lot of space for actually not a lot of information you need to include there, so please don't be intimidated by the amount of space they've left you to write. Question 6.2, let's get rid of that. So we then have to write an equation for the reaction of chlorine with cold water. So we've got an equation for the reaction of chlorine with cold water. So chlorine existing as Cl2, water existing as H2O. So our equation, Cl2 plus H2O. It's actually a reversible reaction, this, and it will produce for us hydrogen chlorate, HClO, and HCl. Now, they want to know the reason we add chlorine to drinking water. Well, the main idea being that it is going to kill bacteria, allowing it to be potable, allowing us to drink that water. Now, what would be a disadvantage of that? Well, if the chlorine is too concentrated, it can be toxic. There are a couple of others they will accept on the mark scheme. So again, I would actively encourage you to have a look in the mark scheme at those. We've then got bromine reacts with phosphorus, so Br2, remembering that phosphorus is P4, to form phosphorus tribromide. Now the suggestion here being that tribromide would be 3. Write an equation for the reaction and draw the shape of the phosphorus tribromide molecule formed. Suggest the bond angle. So our equation here then, we've already got Br2 and P4 to make PBr3. I'm going to need to balance this. So I've got 4 P's, so I'm going to need 4 PBr3, which gives us 12 Brs, so 6 Br2s. The shape here then, well, looking at my periodic table, I can see that phosphorus has got 5 electrons on its outside shell. It's then bonded to 3 bromines, meaning that it's going to have a total of 8 electrons around it, and there will be 4 pairs. Now, one of those pairs must be a lone pair. So I'm going to start with my P. I'm going to make sure I show my BRs in 3D. So using my wedges and my hashed lines. And I'm going to make sure I label my lone pair. So it should look a little something like that. Now the bond angle is going to be slightly reduced because these electrons are going to be repelling the bonding pairs of electrons. So it should end up at around 107 degrees. The next one then, we're asked to then look at phosphorus pentabromide. So phosphorus pentabromide in the solid state consists of PbBr4+. We have to draw the shape of the PbBr4+ and suggest its bond angle. Now this time then, we know that P had 5 electrons in its outside shell, but because it's a positive ion, there are going to be 4. There are then 4 Brs surrounding it, so a total of 8 electrons around the P. Now, because we've got 4 Brs, we're not going to have a lone pair. If I start with my P in the middle. We're not going to have a lone pair, but we are going to have 4 Brs attached in a tetrahedral shape. This will then lead to a bond angle of 109.5 degrees.